Greetings and salutations, everybody. This is Jacob. Okay, so how do we go about solving this problem? Seems complicated. Okay, first we're going to have to figure out the radius r of the two static circles. Note this triangle here, ABC. We'll call this angle here theta. Let's try to figure out theta. We'll use the law of cosines for this, which is AB squared equals 3/2 AB squared plus 3/2 AB squared minus 2 times 3/2 AB times 3/2 AB times cosine of theta. We do the calculations, all the algebraic operations. The ABs, as you see, they cancel out, and we end up with theta approximately 38.94 degrees. All right, so what can we do with this angle here? We'll use the double angle theorem, which says that the angle at the center of a circle is double that at the circumference. Hence, this angle here is 77.88 degrees. Now, let's turn our attention to the bigger circle, specifically this angle here that leads to the common chord AB. We'll use the perpendicular bisector theorem here, which says the perpendicular bisector of a chord passes through the center of the circle. So we'll draw such a line segment. And since it bisects the line segment AB into two equal halves, it also cuts this angle here in two equal halves. We'll call this smaller angle theta 1. So let's turn our attention here to this triangle here, ADF. We know from trigonometry that sine of theta 1 equals AB over 2 all over 2r. And from this triangle here, AGF, we have sine of 38.94 degrees equals AB over 2 all over r. So let's divide these two equations, and we get sine of theta 1 over sine of 38.94 degrees equals AB over 4r over AB over 2r. The AB's and the r's cancel out, and then all this equals 1/2. So sine of theta 1 equals sine of 38.94 degrees over 2, which is theta 1 equals arc sine of 38.94 over 2, which is approximately 18.31 degrees. So this entire angle here is 2 times 18.31, which is 36.62 degrees. Okay, now we have the angles at the center of each circle, which look to the common chord AB. What can we do with this information? Well, we know the total area of the overlap, which is 3 square meters, and the area of this overlap is the area of this segment here, plus the area of this segment here. Now we'll use a formula for the area of a circle segment, and the area now becomes 77.88 times pi over 360 minus sine of 77.88 degrees over 2 times r squared plus 36.62 times pi over 360 minus sine of 36.62 degrees over 2 times 2r squared equals 3. And we do the calculations and all the algebraic operations, and we end up with r equals 3.33 meters. Okay, now that we found the radius of the two circles, now we can turn our attention to the rolling circle. So let's assume it starts its journey at this point here. It doesn't matter where it starts and stops, as long as it's the same point. So for starters, let's turn our attention to this triangle here that joins the three centers of the circles, DHG. DH is 2r plus 1, which is 7.66. HG is r plus 1, which is 4.33 meters. But what is DG? Since the static circles overlap, we can't just add up the radiuses, so we're going to have to find DG. Let's turn our attention back to the triangle ADG. Since the sum of all three angles of a triangle is 180 degrees, this angle here is 122.75 degrees. Using the law of sines, we have AG over sine of 18.31 degrees equals DG over sine of 122.75 degrees, which is DG equals 3.33 times 0.841 all over 0.314, which is 8.9 meters. So now we have all three sides of this triangle here. What we really need is these two angles here. We'll call them theta 2 and theta 3. So we'll use the law of cosines again to find theta 2 first. So we have 4.33 squared equals 7.66 squared plus 8.9 squared minus 2 times 7.66 times 8.9 times cosine of theta 2, which is cosine of theta 2 equals 58.67 plus 79.21 minus 18.74 all over 2 times 7.66 times 8.9, which is 0.87, which is theta 2 equals arc cosine of 0.87, which is 29.54 degrees. Now let's find theta 3 using the law of sines this time. 4.33 over sine of 29.54 equals 7.66 over sine of theta 3. So sine of theta 3 is 0.87, which is theta 3 equals arc sine of 0.87, which is 60.45 degrees. Okay, we found the critical angles. Now we can figure out the revolutions of the rolling circle. So the revolutions a circle makes around its axis is the distance the center of mass traverses, which is the center of the circle, divided by its circumference. So when the center, for example, traverses 2 pi r distance, the circle has made 1 revolution around its axis. So the total revolutions this rolling circle makes is a revolution it makes when it's on the bigger circle, plus the revolutions it makes when it's on the smaller circle. So let's calculate the former first. Let's find the distance the center of the rolling circle makes when it revolves around the bigger circle. The distance is the arc length of this bigger circle here. The formula for the arc length of a circle sector is L equals theta times pi times r all over 180, and theta is in degrees. So this big angle here is 360 minus 2 times theta 2, which is 360 minus 2 times 29.54, which is 300.92 degrees. And this other big angle here is 360 minus 2 times theta 3, which is 239.1 degrees. So the total amount of revolutions that the rolling circle makes around the combined circumference of the static circles is 300.92 times pi times 7.66 over 360 pi plus 239.1 times pi times 4.33 all over 360 pi, and this equals 9.27 revolutions around its axis. 9.27. I'm not going to say that was an intuitive answer. My intuition can't make heads or tails of this problem, to be honest with you. So yeah, that was a pretty long-winded problem, if you ask me. I made this problem myself, by the way. Yep, it's a homegrown problem, but I didn't anticipate it being this long. If I anticipated it, then I would have shortened it a bit. It's quite a monstrosity. I'm sure this is going to be my longest video. Even just the static part of this problem is a good geometry puzzle in itself. But I really wanted to do something with a rolling circle, so I threw that in there. Let me know if you found this difficult. I like to keep the average difficulty of a problem on this channel at a reasonable level, so your feedback is valuable. I hope you liked it. It was a sort of a physics geometry hybrid problem because it involves motion, you know. From now on, you'll be seeing a lot of these types of hybrid problems on my channel, combining seemingly disparate areas of mathematics and physics. I like to make connections between things that seemingly have no connections. That's part of the joy of having this channel, you know. So put the smackdown on the like, subscribe, and the notification buttons if you like this puzzle. And share the video with a friend. More goodies on the way, guys. Logic, algebra, geometry, physics, combinatorics, calculus, differential equations, optimization, set theory, chess, probability will be the main areas of focus on this channel. So, if you made it this far, then I commend your attention span. Take care, you guys, and I'll see you in the next video. Bye-bye.